Okay, we are going to do the 2022 set for states of matter. We're done with 2023. Part D says 3.30 grams of sample of period 3 chloride. Period 3 chlorides, you know what they are. It's NaCl, it can be MgCl2, it can be Al2Cl6, it can be PCl5, it can be, all of these SiCl4, it can be any of these, this fella. Now it's saying that this mass is heated to 500 Kelvin in a sealed container, sealed flask. At this temperature, the chloride is a gas of a volume 250 cm cube, and the pressure of the flask is this much. Use the ideal gas equation to calculate the MR. Now, I've given you guys the idea. You can calculate it directly using the expression, which is right here. You can calculate the MR using this particular expression, or you could calculate the moles first and then use mole equal mass times MR, mass equal mole times MR, and actually calculate the MR for it. But you could even manipulate this equation, PV equals nRT, and mass equal mole times molar mass, or mole times MR, right? So if you want to figure out the moles from this, if I were to make moles the subject of this equation, it'll be mass divided by MR. And so you could plug this fella right here. So you're going to get PV equals mRT, where M is the mass, divided by MR. And this MR goes on the left hand side. So you get MR equals mRT divided by PV. You could actually calculate the MR directly by using this particular equation, or you could first find the moles and use mass equal mole times molar mass, or mass equal mole times MR, and actually get the MR. It's up to you. I'm going to use the first case scenario, right? You could do either or, it doesn't really make a difference, right? So PV equals nRT, and I'm going to say, hey, I manipulated this equation, which is PV equals, instead of N, I'm saying mass RT divided by MR, and then MR equals mRT divided by PV. And what is the MR, sir? Let's calculate it. Pressure is given to me, which is 323 kilopascals, and kilo literally means 323 kilopascals, and kilo literally means 10 raised to the power 3. So 323 into 10 raised to the power 3, because it's 1000, into volume. Volume is in centimeter cube, converted into meter cube, which is multiplied by 10 raised to the power minus 6, and we did this, right? 1 meter equals 100 centimeter. So if I were to calculate 1 meter cube, it would be 1 million cm cube. So if I were to convert 250 cm cube into meter cube, you would get 250 divided by 10 raised to the power 6, or 250 into 10 raised to the power minus 6. The same thing. Divide by 10 raised to the power 6 minus 6. Divide by 1 million, or multiplied by 10 raised to the power minus 6 is the same idea. And what is mass is given to you, 3.30. What is R? It's 8.31. What is temperature? Temperature is 500 Kelvin. What do you get, sir? MR? Use the expression, calculate it, sir. What do you get as your MR? This particular expression contains marks. That's why I did it like this. These expressions are actually the ones that will give you the mark. This expression is the one that will give you the mark. So if you want to get full marks, it's good to use these expressions. It's important. So we get what? 169.8. Great stuff. Now, understand that all the data that's given to you in the question, has he said write it correct to 3 sig fig? No, he hasn't. But even if he hasn't written it right correct to 3 significant figures, I will still write it correct to 3 sig fig. Why? Because all the data that has been given to me, 1, 2, 3, 3 sig fig, 3 sig fig, 3 sig fig, 3 sig fig, all the data that's been given to me is 3 sig fig. I can't possibly get a more accurate data than 3 sig fig. I can't get 4 significant figures. I can't possibly do that, because you know that the significant figures that you write your answer to should be the one that's given in the question, because your answer can't be more accurate than the measurements that you've taken in the laboratory. Isn't that true? Your answer will be as accurate as the measurements you've taken in the laboratory. So it can't be 169.8. It should be incorrect to 3 sig fig, and therefore this 8 should be rounded off, and 170 should be the MR. And this is where students lose marks when it comes to these particular questions. These questions are very simple, very basic, straightforward questions, but they lose marks when they write down the final answer. And what's the formula for period 3 chloride? So if you want to figure it out, which particular fella will have an MR of 170, you can calculate this, 23 plus 35.5, keep on adding them and keep on checking. And I think, if I'm not wrong, it's SiCl4, because if we check out the mass of Si, that's 28.1 in the periodic table. Chlorine is 35.5, times it by 4. What do you get? I think you get roughly around 170. I think If you guys do this, what do you get? You get 170.1. So roughly around 170, right? So it's this fella, because he said it's a period 3 chloride. He stated it right here. It's a period 3 chloride right here. So it should be either of these fellas, and it's SiCl4 therefore, because it fits the MR, right? So we had to do this through trial and error. That's it. Done. Next question. Now this question is wrongly added by whoever was making or compiling this. I did not add this question in this particular chapter, but if it's added, I'll solve it here. But please, after you do chapter number 10, you'll be able to solve this question. So for now, you guys need to skip out on this question. After you do chapter 10, you can come back and watch this particular lecture. But because it's in the booklet, I will solve it right away. You guys have to see it after you do reaction kinetics with me. So it says figure 3.2 shows Boltzmann distribution of energies for molecules of G at constant temperature T. And he says sketch on figure 3.2 the Boltzmann distribution of energies for molecules of G at a higher temperature. Whenever it's a higher temperature, we know that the peak drops and the graph spreads. It drops and spreads, drops, spreads. And we've learned all the idea behind it in chapter number 10. After you do chapter number 10, you'll also be able to know this, right? So the peak drops and the graph spreads, right? So it looks something like this. This is how it looks. Sorry for my pathetic drawing, but this is how it looks, right? And I can even prove it to you. See, this is the peak. This is Y1. And in this case, the peak is right here. This is the new peak. So the peak drops and the x-axis spreads. This was x1, and see, you have, and this is just extra drawing for you guys. See, so the graph has spread, it has shifted, and the peak has dropped, right? Because the number of molecules need to be the same in both these cases, right? So you have to make sure that if you were to spread the graph, the peak must drop in order for the number of molecules to be the same, because with temperature, the molecules don't change, do they? So the graph spread it we went from x1 to x2, we shifted to the right, and the peak dropped from y1 to y2, right? And if you look at the energies now, the activation energy now is this much. The molecules that have greater energy is now this much. Right? This is the activation energy. More molecules now have energy greater than the EA for at higher temperatures, right? So you'll know, you'll figure this out when you do chapter number 10. And the examiner report has said, and I quote, that this particular question was poorly attempted by a lot of students. Poorly, very poorly. Done. Question, the 2022 set is over.